Alright, hey guys, what is going on? We are now going to talk about the Viasoro algebra, or Viasoro. I don't know how this is pronounced, but I say Viasoro. Correct me if I'm wrong. The Viasoro algebra within the context of conformal field theory is super interesting, right? Because so we've talked about the Witt algebra, and now we're going to quantize the Witt algebra. And what we're going to find is something quite interesting and unique about this algebra that kind of corresponds to something that we've seen in the unified conformal field theory. Here's the point, right? So I'm sorry, what I've decided to do recently is get to the point before we actually start the video, because I realize that for those of you who are not contributing to the channel, I still want to give you what the point is so that when you go into the next video, you don't lose any information. You just lose, what you don't get is some of the details that you would get if you become a member. So here's the point. So we've talked about conformal algebra. We've talked about doing the 2D CFT and how that corresponds to the Witt algebra, how that gives us the Witt algebra. We've talked about also conformal algebra. We've talked about unifying all these operators into these J generators, okay? And then from the unified CFT, we've been able to generate or reconstruct the Lorentz algebra. Okay, now what we're going to do is we're going to use the Jacobi identity for the Witt algebra to ensure that the quantum version of the Witt algebra is a Lie algebra. And that new algebra is going to be the Viasoro algebra, or the Viasoro algebra. Again, if I'm pronouncing this wrong, correct me on the chat or on the comments. And what we'll see also is that when we do this process, what we're going to find is that there's a very interesting analogy that can be made between the unified CFT and the Viasoro algebra. So that's what we're going to see here. So with all of that being said, let's go ahead and now get started in quantizing the Witt algebra. Again, if you like this kind of content, make sure to hit that like and subscribe. You can go on to my Patreon if you want to contribute there. You can also go on or become a member here on YouTube and contribute in that way as well. All right, so the Viasoro algebra is the next best thing that we can get from the Witt algebra. What we're going to do here is we're going to add an interesting term here to the Witt algebra called the central extension of the algebra. Let's recall what the subscripts mean really quick, because we don't want to lose sight of these. The subscripts are labels that are going to refer to translations, rotations, dilations, and special conformal transformations within the context of the complex plane, okay? And so this is their corresponding generator. This is what they all represent. This is all the transformation types that they represent at each value, and the small shift is going to represent these things right here, right? So we have shifting when n equals 1. We have scaling and phase shifting when n equals 0. And we have inversion like local distortions. That's going to be the special conformal transformations. So we've talked about this already, okay? So suppose now we wanted to look at translations commuted with special conformal transformations. The sum of the n values is 0 for each transformation, okay? Let's take a look at what this means, right? So just pictorially, sort of trying to understand this, we have, if we take n equals -1 and n equals 1, that's going to be translation special conformal transformation. The sum of these guys, n plus minus, or 1 plus -1, that's 0. Okay? And then we can have 1, so we can have anything greater than 1, so like 2 plus or minus -2. Well, that's going to be 0 as well. So what this Viasoro algebra is going to do, or Viasoro algebra is going to do, is it's going to look for specific n values, okay, and it's going to add a central extension term to that, okay? So let's see how this works. With this picture in mind, we can see that dilations and rotations are unique in that when commuted with anything else, the result is a scale multiple of another element within the algebra. So let's flesh out what all of these commuters are for the Witt algebra. So we can plug in n equals -1, n equals -1 here, and m equals -1. And what we get is n plus m, right? So -1 plus -1. That's going to be -1 minus 1. Okay. Excuse me. But then we have this -1 plus 1 here, right? Because that was part of our Witt algebra. So what we have is a translation and a translation, right? Because we have n equals -1's translations. That's going to give us 0, right? Because this thing goes to 0. And you could do the same thing for a lot of these. And what I did here is I said, okay, so you have, these are all for the first element being translations. These are all for the first element being dilations and rotations. And then these are all for the first element being special conformal transformations. And so I've written that all out here, okay? And there's a method to my madness, right? The idea here is that we want to put names to these operators so we don't lose sight of what they actually represent. Okay, so we're going to define a central extension term now, and this is going to be a function of m and n, right? So m and n. And so it's going to look for certain m values, and it's going to look for certain n values, and it's going to add a term accordingly. So this kmn is just a number, and it does not change. So we can imagine, however, this constant focusing on a certain pair of operators depending on what m and n are. So we can imagine if this was a Kronecker delta, for example, then some of these are going to get excluded. This term is just going to go to 0, and we just recover the Witt algebra. All right? We'll call that equation 1. All right. The function could, for example, search for a set of operators or operator pairs within these commutation relationships and only affect their commutation relationship. The following relationships are the ones where m plus n equals 0. So 1 plus -1, that's 0. 0 plus 0, that's 0. 1 plus -1 again is 0. So what are these ones? This is translation, special conformal, translation, special conformal, rotation, dilation, rotations, dilations. That's what we have here. Excuse me. We can notice that anything with the special conformal other than itself is going, so we have translation, special conformal, translation, special conformal. So, and then we have these guys here. So if we have a Kronecker delta that somehow involves these guys in there, we'll be excluding these guys, okay? And also this one here. Okay. So far, so good. We haven't really done much yet. But with this in mind, we can now turn to the Vias-Soro algebra. The central extension term can be any function, though, in order to preserve the Lie algebra structure. Right? If you just add a number to the Lie algebra, nothing really changes. It's still a Lie algebra. You just have this additional number here. What we'll do in this discussion is explicitly derive the form of the central term and in order for the Vias-Soro algebra to work as a Lie algebra. Okay, because there's many constraints that have to occur in order for this to be a Lie algebra, right? The Lie algebra has many constraints, has quite a few constraints on it. The constraint is going to come in the form of the Jacobi identity. So this is our Jacobi identity. This is something that has to be met in order for a Lie algebra to be, in order for a Lie algebra to be a Lie algebra, right? So this is the Jacobi identity, and so we could focus on the first term of the Jacobi identity, and we could see that with equation 1, going back here, this guy here, we're proposing the central term. We can get this here, right? So we just take m with n right? M with n plus p, right? Because we have this p here. If you're not aware of how commutations work, there's plenty of videos on YouTube showing this, but there's also, I believe I don't know if I talked about this in any of my playlists, but we won't go too deep into this, but this here is going to be m and n plus p, and then m and n plus p, or n and p in the central term. And so this is just a function, right? And so this is going to be 0. This k is just a function. And so what we get is this. All right. All right. So expanding equation 1, right? So again, equation 1 is right here. We'll keep on reminding ourselves this equation. Equation 1, what we get is this right here, right? So we're putting n plus p in, right? So n plus p, so here's our n plus p. Actually, let me look at that really quick. Oh yeah, because we have n plus p in here as well. So n plus p has to get put in here. And so then we have this m minus n plus p, right? Because we have m minus this. So wherever, basically what's happening is wherever n is, we put n plus p, or n minus p. All right. Okay, so the Jacobi identity then becomes this right here, right? Because we take our Jacobi identity, we have this here, so we can write all of this. We just literally plug this in to here, and then this enables us to calculate this, which we can then put in onto all of these guys, right? So just for the sake, you could pause the video if you want to see how this all works, but everything should be good here. Everything should be kosher. But this is what we get. And then from here to here, then, we have two equations, right? And the two equations are, well, everything that multiplies by L is here. And that all has to go to 0 in order for this to be 0. And everything that multiplies by K also has to be 0, in order for this to be 0. So we now aim to solve for the central extension term. Let's propose the following solution. It's going to look like some function. We haven't really done much to k here, but we've added this delta function here, this m plus n, and so this is where we start alluding to this right here, this m plus n and 0. So whenever m plus n is equal to 0, Kronecker delta is going to be Kronecker of 0, 0, and the central extension term, therefore, is searching for special conformal transformations. Right? And the translations, and adds an arbitrary function f of m to their commutation relationship. Recall how this was done with the unified CFT. Right? So if you want now to contribute to the channel, this is where you'll be able to do that. Because this is where things get really interesting and kind of difficult to understand a little bit. And so if you want to understand how there's an analogy between the unified CFT and what we're doing here, and understanding how this we were able to quantize things to get the Witt algebra, you can become a member. Right? So with that being said, make sure to hit that like and subscribe button, and I will see you guys in the next video. Again, this is good stuff, right? So make sure to become a member.